A great day, everyone. Today we are to talk about the Centrosome Cycle. In the nucleus of each cell, the DNA molecule is packaged into thread-like structures called chromosomes. Each chromosome is made up of DNA tightly coiled, many times around proteins called histones that support its structure. The centrosomes are the major microtubules organizing centers of animal cells. These small organelles participate in diverse cellular functions such as cell division, polarity, migration, and signaling, and are often regulated in diseases such as cancer and macrocephaly. Remember, the chromosomes are not visible in the cell's nucleus, not even under the microscope, when the cell is not dividing. However, the DNA that makes up chromosomes becomes more tightly packed during cell division and is then visible under a microscope. Most of what researchers know about chromosomes was learned by observing chromosomes during cell division. Let us consider a figure with the structure of a chromosome. A chromosome may be classified or identified as, or characterized rather, as rod-shaped strands composed of chromosomes, chromatin, a complex mixture of protein and DNA. Each chromosome is a very long strand composed of many nucleotides. Human cells contain 23 pairs of homologous chromosomes, 46 in all. Male contains a shorter Y chromosome and X. Females only have X chromosomes, so that dictates the gender of the offspring. Over the past few decades, technical advances enable a deeper knowledge of the molecular composition and mechanisms of centrosome assembly and function. These progresses also allowed a better understanding of how this centrosome cycle is coordinated with the cell cycle to ensure that centrosomes duplicate once and only once. The discoveries, together with the emergence of in vivo models of centrosome deregulation, have consolidated the 100-year pioneer view of Theodore Boveri about the role of centrosome amplification in abnormal cell division, tumorigenesis, and developmental diseases such as macrocephaly. Figure 2 gives us an overview of the centrosome structure and functions. The schematic presentation of the canonical mother-daughter central pair in most animal cells in 3D is presented. Each centrosome comprises one mother, that is the older, and one daughter, the newly formed centriole, which are surrounded by a proteinaceous matrix, the pericentriole material, PCM, depicted in blue, and the centriolar satellites, electron-dense cytoplasmic granules, contain several chromosomal proteins, represented in gray. Centrioles are barrel-shaped structures made of 9 microtubules, triples, measures approximately 500 nanometer in height and 250 nanometer in diameter. Please note that only mother centrioles possess subdistal, that is the pink, and distal, identified as the purple appendages, which are important for cytoplasmic empties, docking, and cilia formation, respectively. Chromosomes participate in many cellular processes such as cell proliferation, polarity, migration, sensing, and signaling. The second aspect is the schematic representation of longitudinal and cross-sections of the central cord. The part wheel presents only in daughter centrioles. It's made up of 22 nanometer central hub from which 9 spokes emanate and the pinheads. The pinhead structure links spokes to the A and T. Figure 3 gives us an overview of the centrosome cycle. During S phase, one procentriole forms perpendicularly to the proximal part of each pre-existing centriole, the procentriole formation. Extra duplication rounds are inhibited until the following S phase. Procentral elongation occurs between S phase and mitosis. At the end of G2 phase, centrosome accumulates more pericentrioral material, that is the centrosome maturation, and separates the loss of the linker between the two chromosomes, yellow line, indicated. In mitosis, each centrosome migrates to opposite poles of the cell, allowing proper spindle organization. Finally, centrioles disengage during anaphase. Centrosomes are not only the main microtubule organizers of animal cells, but also acting organizer centers. Centriole duplication occurs only once per cell cycle and is triggered by a core module composed of PLK4, SAS6, SDIL proteins. Regulation of the level of these components is critical to control central number in cells. Figure 4 gives us the major regulators of central biogenesis. The initiation of central biogenesis starts with the recruitment of PLK4 at the procentral nucleation site. This process is dependent on CEP63, CEP152, and CEP192 in humans and allow SAS6 and SDIL recruitment and maintenance essentials. Therefore, enabling particle formation, SAS6 and SDIL are essential for CPAP recruitment to the central, with the latter being thought to reduce MT incorporation to centrioles. Subsequently, procentral elongation is promoted mostly by CPAP, CEP120, and CEP135, and restricted by CEP110, CEP97. Centrosome duplication and cell cycle progression is tightly coupled and share common regulators. Centrosome loss and amplification can lead to abnormal mitotic spindle formation, chromosome instability, and cell cycle arrest. Centrosome amplification leads to tumorigenesis and microcephaly. Figure 5, centrosome amplification and diseases are presented. In this figure, centrosome abnormalities, for example, centrosome amplification, more than 2 centrosomes per cycle are involved in several diseases such as microcephaly and cancer. Supernumerically, centrosomes might trigger tumor formation by promoting chromosomal instability and/or invasiveness. Centrosome amplification might cause microcephaly by diminishing the mutants and cell pool. That's it for today. Thank you.